A back-illuminated sensor, also known as backside illumination sensor, is a type of digital image sensor that uses a novel arrangement of the imaging elements to increase the amount of light captured and thereby improve low-light performance. The technique was used for some time in specialized roles like low-light security cameras and astronomy sensors, but was complex to build and required further refinement to become widely used. Sony was the first to reduce these problems and their costs sufficiently to introduce a 5-megapixel 1.75 AA micrometer BI CMOS sensor at general consumer prices in 2009. BI sensors from OmniVision Technologies have since been used in consumer electronics from other manufacturers as in the HTC EVO 4G, Android smartphone, and as a major selling point for the camera in Apple's iPhone 4. Description: a traditional, front-illuminated digital camera is constructed in a fashion similar to the human eye, with a lens at the front, wiring in the middle, and photodetectors at the back. This traditional orientation of the sensor places the active matrix of the digital camera image sensor a matrix of individual picture elements on its front surface and simplifies manufacturing. The matrix and its wiring, however, reflect some of the light, and thus the photocathode layer can only receive the remainder of the incoming light. The reflection reduces the signal that is available to be captured. A back-illuminated sensor contains the same elements, but orientates the wiring behind the photocathode layer by flipping the silicon wafer during manufacturing and then thinning its reverse side so that light can strike the photocathode layer without passing through the wiring layer. This change can improve the chance of an input photon being captured from about 60% to over 90%, with the greatest difference realized when pixel size is small, as the light capture area gained in moving the wiring from the top to bottom surface is proportionately smaller for a larger pixel. BSI CMOS sensors are most advantageous in partial sun and other low-light conditions. Placing the wiring behind the light sensors is similar to the difference between a cephalopod eye and a vertebrate eye. Orienting the active matrix transistors behind the photocathode layer can lead to a host of problems, such as crosstalk, which causes noise, dark current, and color mixing between adjacent pixels. Thinning also makes the silicon wafer more fragile. These problems could be solved through improved manufacturing processes, but only at the cost of lower yields, and consequently higher prices. Despite these issues, early BI sensors found uses in niche roles where their better low-light performance was important. Early uses included industrial sensors, security cameras, microscope cameras and astronomy systems. Industry observers noted that a back-illuminated sensor could theoretically cost less than a similar front-illuminated version. The ability to collect more light meant that a similarly sized sensor array could offer higher resolution without the drop in low-light performance otherwise associated with the megapixel race. Alternatively, the same resolution and low-light capability could be offered on a smaller chip, lowering costs. Key to attaining these advantages would be an improved process that addressed the yield problems, largely through improving the uniformity of an active layer on the front of the detectors. A major step in the adoption of BI sensors was made when OmniVision Technologies sampled their first sensors using the technique in 2007. These sensors, however, did not see widespread use due to their high costs. Sony's work on new photodiode materials and processes allowed them to introduce the first consumer back-illuminated sensor as their CMOS-based XMR in August 2009. According to Sony, the new material offered +8 dB signaling and a 2 dB noise. When combined with the new back-illuminated layout, the sensor improved low-light performance by as much as 2 times. Competitors followed suit, and by the end of the year most companies were offering a version in their high-end products. OmniVision has continued to push the technology down their product lines. By contrast, the iPhone 4 employs a sensor manufactured by Sony. Another example is the HTC EVO 4G, which equipped with an 8MP x 1.4 AA micrometer pixel BSI sensor from OmniVision. In 2011, Sony implemented their XMR sensor in their flagship smartphone Sony Ericsson XPERIA Arcade. In January 2012, Sony developed the backside illuminated sensor further with stacked CMOS, where the supporting circuitry is moved below the active pixel section, giving another 30% improvement to light capturing capability. This was commercialized by Sony in August 2012 as XMOS with resolutions of 13 and 8 effective megapixels. In September 2014, Samsung announced the world's first APS-C sensor to adopt backside illuminated pixel technology. This 28 megapixel sensor was adopted by their new compact system camera, the NX1, and was showcased along with the camera at Photokina 2014, held in Cologne, Germany, September 16 to 21. See also, wafer back grinding, references, notes. Bibliography. External links.